Alright, so in this video, I'm gonna be explaining this representation learning of geometric trees. In nature, we have some geometric graphs, like in chemistry, when we have a molecule, there are some angles between different bonds, and so these are so the angle between them is very important. And so we want to learn these things so that, because many of these rotations are group invariant, so we want to preserve these invariants. For example, in geometric trees, that is the focus of this paper, we will see that there are like rivers or different kinds of things that you see in nature that have some angles between the edges. And so we want to take advantage of these to have better and more efficient deep learning with probably less nodes, less neurons, in order to encode these information. So geometric trees are characterized by their tree-structured layout and spatially constrained nodes and edges. So the location, even the distance between nodes, the angle, the distance, all of these are important, which significantly impacts their topological attributes. This inherent hierarchical structure plays a crucial role in domains such as neuron morphology and river geomorphology, but traditional graph representation methods often overlook these specific characteristics of tree structures. To address this, we introduce a new representation learning framework tailored for geometric trees. It first features a unique message passing neural network, which is both provably geometrical structure recoverable and rotation translation invariant. To address the data label scarcity issue, our approach also includes two innovative training targets that reflect the hierarchical ordering and geometric structure of these geometric trees. This enables fully self-supervised learning without explicit labels. So this is an illustration of neurons, geometric, tree-like. And in B, you will see representation of a river network exhibiting a tree structure embedded within a geometric landscape. Traditionally, when people talk about deep learning and when you want an introductory course to neural network, they never talk about these angles or the distance between these two nodes. They never talk about it. But in geometric trees, these angles, distances, all of these things are important geometric features that if we leverage them, then we can efficiently encode our information. What is our information? Our feature space, with probably less number of neurons to learn them. So a geometric tree is a hierarchically arranged tree-structured graph with nodes and edges that are spatially constrained, influencing their connectivity pattern. It is particularly important data structure that is ubiquitous in different domains such as geomorphology, neuron morphology. So how do we reflect the hierarchical patterns of geometric trees in the learned representation? And another question, how do we learn the representation with label scarcity? Another important question, how do we represent the nodes and its geometric and topological context in geometric trees? So they talk about geometric tree branch message passing. So to develop a novel geometric tree representation method by addressing the challenges outlined above, we propose a new representation learning model named Geometric Tree Branch Message Passing. This scenario preserves the geometric structure of tree information with theoretical guarantees on the invariance to spatial invariant SE3 symmetric transformation and spatial information lossless. To incorporate the underlying hierarchical relationship, a partial ordering constraints over parent-child pair embeddings is introduced. So the spatial information of a geometric tree with n nodes can be expressed as a set of Cartesian coordinates. So we have x, y, z, and then we have a length. Given a length tree branch, the proposed spatial information can be expressed like this. So some of them are angles, some of them are just distances. So a length 3 branch, for example, we go from v sub I to v sub j to v sub k and then v sub p can be expressed as pijkp, where vi is the parent node of vj, vj is parent node of vk, v sub k is the parent node of v sub p. So you get that. So for example, theta, of course we have a picture, we will show that. But so this is the way that we can encode these spatial information. The defined distances and angles and torsions exhibit rigorous invariance under any rotation and translation transformation. So we propose the following operation to update the hidden state embedding by aggregating the message passing along all length 3 branches. So along all length 3 branches, for example, this is a length 3 branches, another branch, and another branch. It's like a river. And you will see that we want to update the hidden representation of each node. So by aggregating the messages that is coming, by aggregating all these messages, all 3 branches, we can update. And this sigma here is just an arbitrary nonlinear transformation. Once we get the aggregation of the messages, we can do nonlinear transformation. So the integration of node features with geometric data is accomplished through a function phi sub L, which combines aggregated node features with a transformation of geometric information psi. So these are geometric transformation. The final messages is this. So it's very important to know that this psi is a geometric transformation. And both of them, of course, are 2 nonlinear functions to extract the complicated coupling relationship between geometric and tree topology information. The aggregated node features are computed as a weighted combination of the features from node v sub I and its descendants orders. So you see different branches. For example, here we see 3 branches. They aggregate to update this node v sub I, so the representation of that is h sub I, which is updated. And these angles, all of them are geometric features that we should encode, and they are encoded that in that message passing, which has geometric features. This is an illustration of the hierarchical relationship between three nodes through partial ordering. So T sub k here, T sub k, is a subtree of T sub j, establishing a partial ordering relationship between their respective subtree embedding. So representation of h sub k should be in subset of h sub j, inside h sub j. So this is kind of partial ordering and also corresponding partial representation as well. So this is how we are encoding these information. To accurately represent the inherent hierarchical relationship, we introduce a partial ordering. So to formally define the ordering constraint between node embedding, we introduce the concept of partial ordering, ensuring that hierarchical relationships are accurately represented. For example, in the previous video, I didn't talk about, in their paper, they could also include this kind of partial ordering over subtrees of subtrees like this. It is more interpretable if we do so, but they are focused only on metric embedding on the tree, the distance between nodes and each of these, and also the relative distance. But this one is more. It's like a component. It has substructures, so it has richer information that we need to encapsulate. So if T sub j is a subtree of T sub I, then we have this representation. Then the embedding has to be within the lower left region of node I embedding H sub I. Where D is the dimension of the hidden embedding, and B denotes the Bth dimension of the hidden embedding. So we have D by 1, and for B's row, you will see that we have Hj of B, and the corresponding one should be Hi and B. This one should be less than that. So it makes sense. To operationalize the above constraint into a function that can be optimized, we accordingly define the objective function for generating embedding to utilize the max margin loss. So because we want to preserve this information, so why not using it explicitly in the loss? Because if we say this, it is enforcing to Hj to be less than Hi, H sub j to be less than H sub I, then this one becomes negative and the maximum is 0. So the loss is small, 0 is small. Otherwise the loss increases, so we want to make sure that the loss does not increase. And if the loss decreases, it means that the preservation of these relationships is satisfied. And P and N here are just set of positive pairs and negative pairs in the mini batch, where tree is a subtree of tree T sub I. The term delta here represents the margin that enforces a minimum distance between the embedding of negative pairs compared to positive pairs. So it's interesting that for each h sub I, h sub j, we are encoding them like this. For example, the highest node in this sub branch in this box is v sub j. So the corresponding tree is this. So the corresponding representation is at j. So for each node we have a representation, but of course satisfies this inner nested structure, and we have done this by using this loss. To tackle the challenge of insufficient training labels in real world, we introduce an innovative geometric tree self-supervised learning. While there are existing self-supervised learning objectives, they are insufficient when applied to geometric trees. The primary limitation is their inability to incorporate both intrinsic hierarchical relationships and couple geometric tree topology information into self-supervised learning objectives. To formalize our approach for a node v sub I with a geometric tree T, we denote C as a set of child nodes and A a set of its ancestor nodes. The objective of our subtree growing process is to accurately predict the geometric structure of child nodes, given both the geometric structure of node itself and that of its ancestors. And G is just a learnable function to synthesize the geometric details of the child nodes based on the aggregated geometric information of V sub I. To represent geometric information in a form that is learnable to pattern recognition, we expand these features into frequency space with radial basis function. So for a given node V sub I with child nodes and distances are expanded like this. So E sub k is just the case radial basis, and mu sub k is here mu sub k is the corresponding distance. To obtain the distribution of geometric features over the radial basis, the ground truth distribution can be denoted like this. K is the number of radial basis functions. Then the estimated distribution is this. So we formulate the objective function using Earth moving the distance. This is an important topic in optimal transport and in mathematics. So the Earth moving distance between them should be minimized. This is the loss of generative. And finally, we add these losses together.